Welcome to Organic Chemistry, where everything on paper makes sense, but then sometimes you get into the lab and it doesn't make sense. I'm going to show you two examples of this. Same reaction. The top example has HBr and an alkene, but we're going to be using a new bottle. Brand new bottle off the shelf. We're going to get the chemistry we expect, all right? So we're going to add our HBr, okay? We're going to make that carbocation that is on the most substituted side, and then we're going to add our bromine there. So remember that our reaction here, we've added bromine, okay, and our hydrogen is going to the least substituted side. This is that Markovnikov addition we've talked about. This does form a racemic product, and that's because we go through that carbocation intermediate. A C+ intermediate. And then your advisor, let's say you've got a research advisor. He's like, hey, I need more of that starting material. Okay, and this is maybe 6 months later. And you go back in, you use the same bottle, but now it's more of like an old bottle. Maybe not 6 months, maybe like a couple years later. Takes a while to get your PhD. Anyway, you go run this reaction again, and then you get a different product. And this is when you want to throw the old bottle of HBr out the window, which would be an environmental hazard. So don't do that. But you can also then get this anti-Markovnikov addition. And it's at this point in time, you're like, I quit. Organic chemistry is magic and blasphemy, and this doesn't make sense. Well, this is what makes it fun. Okay, so actually, a really old bottle of HBr will end up having some peroxides in it. And this is what's actually pushing the reaction through a different mechanism. It can have a peroxide impurity. And so it's this like ROOR. And this thing likes to do radical chemistry. And so you end up not getting the product that you wanted to. You end up getting anti-Markovnikov addition, the bromine added on the least substituted side, okay? Your proton should have been going on the side that already had the most protons, and it didn't. So this makes you quite unhappy. And so let's go over what happens in the presence of HBr and peroxides when we have an alkene. We're going to learn a different type of mechanism with radical arrows. And remember here that most of our reactions are involving these curved arrows with 2 electrons. Radical chemistry involves 1 electron arrows. And I think of these as these little fish hooks. So the end of that arrow is signifying, do I have 2 electrons or 1? The majority of the chemistry you're going to do involves 2 electrons. So if you have peroxides, or if you see, anytime you see like light or sometimes heat, okay? So you're only going to be using radical arrows and mechanisms when you see peroxides, usually will form some radicals. If you see light, sometimes if you see heat, but heat can also go with 2 electron curved arrows. So again, radical chemistry, 1 electron, movement of 1 electron. So let's go through the mechanism of this reaction where you did not get the product you wanted. You ended up getting anti-Markovnikov addition of HBr across an alkene. All right, you might be asking, why am I learning this? And this thought is going to pop up a lot in organic chemistry for you. However, I can tell you that what you're learning, one, is going to teach you the best problem-solving skills I think that you can have by going through this course. Now, here's the second thing that's super cool. Halogens in particular are really important for pharmaceuticals. So many of you might be interested in the medical field of some sort. And these pharmaceuticals many of them have halogens present. And so understanding how do we create a carbon X bond is the fundamentals of most of the drugs that you would prescribe. So I thought it'd be cool for us to look at some really relevant research articles. And so let's do that together. So here I have an article from Frontiers in Chemistry. This was published in 2019. Yeah, 2019. pretty recent. There's so many of them if you just Google halogens and pharmaceuticals. And really what happens is when you're discovering a active pharmaceutical ingredient or an API is you're looking to see what can I adjust on it and how will that interact or change its interaction with a protein. Typically, that's what you're doing. And so if I just like scroll down here, you're going to see something really cool, hopefully. There we go. And so this is showing these different motifs. Here we've got bromine and here's chlorine. Now, these are on aromatic rings and we haven't talked about that yet. That'll be your next course. But in general, halogens are super cool and they interact with proteins in what's called a halogen bond. So it's kind of like hydrogen bonding, but not with a hydrogen, with a halogen. And so learning how do we add these X's or these chlorine, bromines, fluorines, iodines on, not a lot of iodines in pharmaceuticals, but how do we add them to the molecules really important. Let's jump over to another research article. This is from Reaction and Chemical Engineering. And this is, Oliver Capet. So this is someone I followed. He did a lot of microwave synthesis as well. Anyway, he's doing continuous flow. So this is involving a lot of engineering on this side. Like not only how do I do the reactions, but also how do I do them really efficiently, right? I want to do big scales of things. And so here he's looking at examples of halogen containing ranked compounds among the top 10 selling drugs in the US. This is from 2014. The sales are in the brackets. Check this out. Billions of dollars, billions with these halogens that are present on our pharmaceuticals. All right. A lot of these do have fluorine, okay, which is why the continuous flow is of interest. So we talked about fluorine being so reactive, it's like explosive. So like, how do you make those carbon fluorine bonds efficiently? And so there's a lot of cool chemistry involved with that. Distribution of halogens within the structure of naturally occurring compounds. So on the left here, this is really what we're looking at. Chlorine and bromine tends to be more naturally occurring. All right. Agrochemicals are on the right where fluorine is more popular. Synthetic APIs, active pharmaceutical ingredients, have chlorine and bromine in them. And here they are looking at ways that you can do this reaction more efficiently and on larger scale. Continuous flow, meaning you're just pumping out product continuously. Pretty neat. And I want to go over one more thing, just kind of diving in again. This is a review article for molecules, and review articles tend to, they grab a whole lot of recent literature and they pop them all in one review and they analyze them and look at where is the field going. And this is from 2017, very recent, looking at halogen bonding in drug discovery. Well, this halogen bonding thing is super interesting. And so this is one of their first figures saying, hey, halogen bonding is a thing. These halogens can interact with proteins, okay, and they'll affect whether or not a new drug is going to fit into the pocket and do what you want it to do. And so having halogens on the active pharmaceutical ingredients actually aid a lot in whether or not something will be active. And what the identity of that halogen is and where it is on the molecule will affect how it docks into that protein. And my favorite part of this graphic is what you're learning. Look, we have a radical and we have a radical X. We are doing some radical chemistry here as well to make these new CX bonds. Now, we also do them with typical 2-electron movement, not radicals, but this is just one of the ways that you can make these CX bonds. So I'm going to scroll down a little more because I think they have some more halogen bonding interactions with proteins. I just think they look cool. It's like beautiful artwork. The proteins here are these little like curly dudes. Now, most of the proteins are understood by crystallography. And so that's a really fun field, actually. And so we understand how these proteins are folded and such based on crystallography. And you might be learning that in another class. But us understanding how to make a CX bond is important because they're so prevalent in pharmaceuticals. So let's scroll down here. So A is a chlorine forms a halogen bond with main chain oxygen of the protein. So on A here, the green dot here, this is a chlorine and it's hydrogen bonding to this red here, this oxygen. And so it's really neat to think about this interaction really affecting whether or not your pharmaceutical ingredient or your active pharmaceutical ingredient can fit and stick and stay inside an active site in a protein. And so this is why we're learning the fundamentals. We have to understand what a CX bond is. We learned about geometries of molecules. We learned all of that stuff. And that's just the fundamental building blocks of how these chemists in current time are able to think about, well, what if I adjust my structure this way? What if I put my chlorine on this side of my compound? How will it react and affect the reactivity inside this active site on this protein? All right. So there's a lot of chemistry that is involved with halogens, and we're just learning the fundamentals, right? So, but all of this is built upon and what's currently happening, looking at halogens in active pharmaceutical ingredients. So let this just be one of the ways I'm going to keep trying to connect real world things that are happening with what you're learning. Many of the things you're learning, again, are fundamentals, but they're so necessary to everything that's happening in the real time of research right now. So, all right, back to the lecture video. All right, so let's look at this reaction in detail, this one where we use that old bottle of HBr that had some peroxide present. So you're going to be adding the bromine here to the end of the alkene. Okay, so this would be Anitmarkovnikov addition. And there's the same steps we've learned about radical halogenation of alkanes is the same kind of steps here with initiation, propagation, and termination. Now, the initiation is really just where you form your first radical. So here you're going to form a radical. And this doesn't happen that much. It's just the initial step of the reaction. Now, propagation is where the chemistry really occurs, okay? So this is where you are making your product, okay? So this is the majority of the chemistry. So this is the most common step that's happening. It's this radical chain mechanism. And this is where product is formed. And the key here is that one radical then makes a new radical. When we draw this out, you'll see what I mean by this. And termination, this is when we essentially take two radicals and then we get rid of all the radicals, okay? So this is not very common in our reaction mechanism. Most of it's happening in the propagation stage. But sometimes you'll have two radicals that combine. So it essentially, it ends the reaction. So this is why it terminates the reaction. It gets rid of the radicals. I want to bring up another thing about radical stability, and we've talked about this with our radical halogenation of alkanes, but this is the same as carbocation stability. So it mirrors carbocation stability. Where a tertiary radical is more stable than a secondary, which is much, 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 much more stable than a primary, which is a methyl with a radical, unless you're like in space and in a vacuum, I don't believe it forms. All right, and so let's look at this mechanism in detail. We're going to use these three steps. So there's really three steps in a radical mechanism, and then we're going to walk through them with this specific example. Let's draw our product again. We know we're Anitmarkovnikov, so 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5 carbons, and the bromine here we'll add on the end. The hydrogen added on 4. So Anitmarkovnikov, bromine adds to the carbon with the most hydrogens, just opposite of our normal HBr. We have our peroxide. We know we're going to do radical chemistry. The first one for initiation is we have our peroxide. These are really reactive. And what will happen is they can do a homolytic cleavage. So homolytic cleavage, meaning you break this single bond right down the middle. We know single bonds are made of, there's 2 electrons here. So I have 1 electron going to one oxygen and the other electron going to the other oxygen. This is going to give us 2 equivalents of this oxygen radical. Then we can take one of our oxygen radicals and we can enter this propagation step. Now remember, propagation is when we are making sure we start with a radical and then we make another one. So we're going to take this oxygen radical and I'm going to break this HBr bond. Now notice I've drawn the 2 arrows coming together here in the middle. It's because they're making a bond together. And the 2 electrons between the hydrogen and bromine, one is going this way and one is going to our bromine. So if we draw what we have, we now have this alcohol plus we have this bromine radical here. Okay, the next step of our propagation that could happen, this bromine radical could hopefully find our alkene. And this is exactly what happens. We end up reacting it with this bromine radical. Now, when we do this, when we react this alkene with this bromine radical, one of the 2 carbons that are on our alkene, either the end or this middle one, is going to get the bromine. Now, we already know that the bromine is going to go on the end, and we can think about, though, what happens if it was to go on carbon 4? Well, if we had the bromine add here, we would have a primary radical. And this would not be happy. This would not be stable. And so this doesn't happen. Instead, so you can either draw that or you can draw it and maybe cross it out. That doesn't form. Instead, what we'll be doing, we will add the bromine on the end, then we'll have our radical here, which is secondary, much more stable and can form. All right, and so now what we can do is we can keep the propagation going. We're going to do one more propagation step, and then we are going to take our radical that we just formed, that secondary radical, and then we're going to find HBr. And check it out. We have our desired product plus we have a bromine radical, which this can then go back into our propagation step. Okay, and it can come back into this step. So propagation, it just keeps going, keeps going, keeps going. And then eventually we end up getting to the termination step, okay, where this is stopping the reactivity. Eventually, one of the bromine radicals will find another bromine radical. And then you're going to make Br2, okay? That's very rare. You could take any of the radicals you find, and it would, if it combines with one of the other radicals, you're essentially taking 2 radicals to 0 radicals, which means that you are no longer propagating this reaction. So at the end of it, we end up getting our Anitmarkovnikov addition. And the bromine is added to the carbon with the most hydrogens. Now a few more notes with this. Now, this reaction works well with HBr and peroxides. And you'll see different peroxides like tert-butyl peroxide. You could also see a mixed peroxide, could work well as also. But this reaction does not work as you go to different halogens. So let's draw those out actually. So I'm going to draw the ones that don't work. So HI, HCl, HF, these all do not work. And the reason is because the propagation steps must be thermodynamically favored, okay? And so it's very unique with HBr. So HBr, this is where the green light is. This works. For HI, HCl, and HF, the energies don't quite work in our favor. So for HI, what happens is that this I radical, it's just too stable. It's just too stable to really move forward in the reaction. HCl and HF, the problem with these two, now the issue with HCl and HF is that these reactions are endothermic. It requires too much energy. So too much energy is required for these reactions. And we can look at this in detail as far as the thermodynamics and actually calculate out this change in enthalpy in order to determine if this reaction can go. But let's just do a brief comparison. Now, in Gen Chem, you would likely have to calculate all of this out, but this is organic chemistry. I would like for you to understand this on a thermodynamic level, but I won't be asking you to calculate these out. I'm going to focus here on this HX bonds section here, and we can do this by looking at HBr, which has about 88 kilocalories is the strength of this HBr bond. Now, if I look at HI, it's pretty weak, and we know that HI has a much weaker bond because that iodine is very large. That's a very large atom, very long, a longer bond, and it's weaker. Now, this is why it's so low in energy, 71 kilocalories per mole, okay? So the problem, though, is that iodine radical is too stable. Now, then we look at HF and HCl, and notice here 136 and 103 kilocalories per mole. Well, if you calculate out all of the steps, which you can actually go to our mechanism and you can calculate out the energies of all of these steps. Now, I won't be requiring you to do this, but I will signal a practice problem in your book if you enjoy thermodynamics, and I don't know, maybe you do. You are welcome to work through that. And your book actually does a nice job explaining it. But the key here is that HF and HCl, these are much stronger. Okay, these bonds are much stronger. 103 kilocalories per mole for HCl and 136 kilocalories per mole for HF. And this is just highlighting again why these are endothermic reactions. So just remember that this Anitmarkovnikov addition, it's special to HBr and peroxides, okay? So we're only going to be using this to add a bromine here, Anitmarkovnikov, and not a chlorine. All right, and I think that's it for this video, and I will see you in the next video.